Hey everybody, this is Ben Kesnoka, co-founder and partner at Village Global, a network-driven venture firm. And this is our podcast, where we go deep on all things business and technology with world-leading experts.
Hello, everybody. I'm Olga Sergeyevich, the head of investor relations at Village Global. Pleased to introduce our guest today, Michael Hochberg. He is a physicist, former professor, and a founder of 4 successful startup companies in semiconductors and telecommunications. Some of his companies include Luxtera, which was acquired by Cisco in 2019, and Elenion, acquired by Nokia. He won a number of highest awards for young scientists in the United States and Singapore, is an author on over 60 patents, and he's been involved in the creation of over 30 companies in biotech and applications of silicon photonics. In today's conversation, we'll talk about silicon photonics, a high-growth market most people have not heard of, the current state of the semiconductor industry, and operating at the intersection of academia and industry. Michael, welcome to the show.
Thank you very much.
So let's start with an overview of your career. Tell us a little bit about some of the key moments of both your academic and private sector careers, inventions, and lessons learned along the way.
Yeah, I'll try to do this briefly and chronologically and as entertaining a way as I can. I grew up in Palo Alto, primarily, at least, when I was a kid in elementary and middle school. And then my parents decided to move to Louisiana when I was in high school. And so when I was in high school, when I was in middle school, I did all sorts of things, building computers, fiddling with computers. And I worked in the family business, which was a company called Stratfor that did geopolitical risk analysis. And that was a lot of fun. And I always found myself attracted to doing whatever the hardest projects were that I could find. So I decided to go to Caltech because I figured Caltech was the place where I could fail the fastest at a career like that. And it did not take me long to fail at that. I went to Caltech and I discovered that unlike the rooms that I had been in high school, where I was among the best people when it came to mathematics, maybe often the best in the room, I got to Caltech and I was firmly below average. And that's kind of the kindest thing I could say about my mathematical skills. I had done many, many years of math, beyond calculus. And I had the immense privilege of retaking all of that math when I got to Caltech. Because I had taken it at the local state college, and the level at which it was being taught was not the level at which I needed to understand it. But yeah, so I went to Caltech and I realized pretty rapidly that I was probably not going to have a career in something like high energy physics. I had done some internships. I spent a summer working at LIGO as a kid, which was really a cool place to work. Those guys were doing, the sheer audacity of what they were doing at LIGO, trying to observe gravitational waves, and the fact that they were essentially measuring nothing. They were just measuring a noise floor for more than a decade and just chipping away at improving the noise floor and improving the noise floor and improving the noise floor until a few years ago they actually started seeing events. People spent their whole career just observing the noise floor. It was an amazing thing to observe, right? We could talk about that.
Fishing.
Yeah, it's certainly kind of, but fantastically expensive and fantastically difficult high precision fishing, right? But so, yeah, I got to Caltech and I realized that my talents probably were better used in a different direction than something that required incredibly high level mathematics. And so I ended up working in first taking a class from and then working in Axel Schurer's lab. He's a semiconductor person, does nano devices, nano optics, all kinds of things that involved building very tiny devices on semiconductor chips. And so basically in my second year, I ended up doing research in his lab and I ended up TAing his class and doing all sorts of fun things in and around his lab. And that summer between my first and second year, I teamed up with my best friend, a guy named Tom Bear Jones, who I've worked with now for close to 25 years. And Tom is a person who did have that kind of mathematical talent and who is a fantastically talented programmer. And we came up with a project where what we wanted to do was to tie together big clusters of Dell machines in order to replicate the performance of a supercomputer, right? And so we did that because with the PCs of the day, you just couldn't get enough memory to actually do the computations that people wanted to run in order to simulate the optical nanostructures that we were building in the lab. And so we put that together. We, Tom actually wrote the code, and we started selling it. And we were selling it for tens of thousands, hundreds of thousands of dollars per seat out of our dorm rooms. We ended up bringing in some venture capital, hiring some people, and building a set of tools that a bunch of people bought and used for many years for electromagnetic simulation. That tool set and that company eventually were what we decided to do. I was up in the Bay Area trying to raise money for a B round for that company. And this investor, his name was John Oxel, and John pointed out that if we had this magical tool for designing optics, that what we should do is take it and use it to design optics. And so we ended up bringing together a team of 6 founders, and the 6 of us started this company called Luxtera. And the basic idea of Luxtera was to take these tools and a bunch of ideas around building optics in silicon, using the same fabrication processes, the same foundries that you would use to make silicon microelectronics, and use it to make optical devices where you could manipulate light on chip. And so Luxtera went on to do that and to build several generations of product and sell a huge number of what are called transceivers, which are the bridge between the electrical domain and the optical domain in data centers. And they've sold huge numbers of those things. They're in probably most of the large scale data centers in the world at this point. I stayed there for about a year after I graduated. We started that effort junior year. And we actually got it funded during the bust after September 11th. So we were one of only a few hardware companies funded in that period. It was really a testament to the commitment of the VCs, to John and to Andy Rappaport, that they really believed in what we were doing and were prepared to fund it when no one was funding anything.
Yep. And reflecting back on some of the lessons of building this company, and many people say hardware is hard, and there's lots of different reasons. So how do you react when you hear something like that? What was actually hard? What was sort of not as hard, maybe, as people say? And what do you think were some of the reasons that the company was successful as it started to scale and grow?
Building any company is hard, right? I mean, and they're building any company, especially any company that's differentiating on technology, is really difficult. And I don't think hardware is intrinsically more difficult than software or than AI or anything else. I think the human dynamics of it are different, right? If you're building a piece of software where you can build a prototype with a small team, and you can do a compile cycle every night, and you can fix bugs, and you can do and you can rev it, relatively frequently, that has a very different flavor to it than something where you design a chip, you tape it out, and you get it back 3 months later. It takes you 3 or 4 months perhaps to test it, and if you got it wrong, you have to go run it through the fab again, do another design cycle. You lose a year, you lose time to market, and you lose a huge amount of money that you need to continue operating your organization for that amount of time, right? So, it's like running a software company where every time you hit compile, it costs 9 to 12 months and tens or hundreds of millions of dollars, right? It's not fundamentally different. It's just very different. I guess the thing that I would say is, there are also different kinds of hardware projects, right? There are hardware projects where you're playing into a very well-defined ecosystem, like if you're taping out electronics to TSMC using software from Cadence and Synopsys and Mentor and the usual suspects. Like that's a very well-defined, very well-trod path. It's a thing that where the ecosystem is well understood, and there's IP that you can license, and there's pieces that you can get off the shelf, and there's a packaging ecosystem and all the rest. One of the things that made Luxtera so hard was that for photonics, that ecosystem was not nearly as mature. So like we were developing a lot of the design tools as we went. And that's been a theme for the last 20 years in silicon photonics. The places that are at the cutting edge often have to develop some of their own design and tape out tools. Just like it was the case in the 70s and 80s and 90s in the digital electronics world. Like the places that were at the cutting edge that were developing the biggest, most complex circuits always were developing some of their own software tools. Like it's not a surprise. It's part of what defines being at the cutting edge, frankly. Less so nowadays in the electronics world, because in the electronics world nowadays, the software is so complicated and so expensive that it's the land of the giants, right? It's Cadence and Synopsys and Mentor and places like that, because there is no startup that could develop that software ecosystem. You might develop a point solution for one particular piece that's unique to you, but the number of tens of billions of dollars that have gone into developing that software is large, right? So, one of the things that I guess one of my key takeaways at Luxtera, and I've seen this again and again, is the quality of the team is the most important thing that you can control as a founder. It's one of the only things that you can control as a founder. If you bring in really first-rate people, and I don't just mean from a technical perspective, I mean people who are technically talented, good at learning new things, emotionally resilient, easy to work with, who the sort of people who can handle adversity and handle things going sideways sometimes. You hire those people, they'll hire other people who are like them, and you'll end up with an organization where even incredibly difficult problems, when the problem walks in your door as a CEO or a founder, the person walking in the door walks in with a solution too, right? Like, hey, here's this incredibly hard problem, and here's how we solved it. Or here, this person did a great job solving this problem and getting out ahead of it. If you hire people who are mediocre, what you will end up with is even trivial problems will be unsolvable. And so, one of the things I was really proud of at Luxtera was, we brought in some really excellent people, and they solved a lot of incredibly hard problems, and across an entire stack where, it wasn't just using some process that TSMC has invented, which is hard enough. It was inventing the process from scratch, and inventing the devices and building all the way up to systems. And so that team, the people on that team, not just at the beginning, but all the way through, that team continued to refresh itself by hiring and training absolutely fantastic people. And that was the core of the company, right? I mean,
let's double click a little bit into the product, the core innovation, core insight about how to scale it. Tell us a little bit about what Luxtera focused on, and what led to success.
I mean, Luxtera was really the first place they were the first place to run optical devices through an honest to God CMOS foundry. This, the same multi-billion-dollar facilities that you use to make microelectronics. And what that allowed Luxtera to do was to have very precise control over the devices. But, Luxtera was very early in the silicon photonics world. Like many of the devices, like when we started Luxtera, many of the basic devices people really hadn't figured out how to make yet. And our VCs at the time referred to what we were doing as a bit of a science project. And at the time, I didn't quite understand what they meant, but in retrospect, it took me a long time to understand what they were talking about. But it was a science project because we really didn't. It wasn't the sort of thing where it's like, all right, lots of people have done something like this before, and it's mostly a question of market fit and execution risk. That was not the case. This was something where we had to invent the devices and then figure out where it could fit into a market, right? Because there was a vision of fitting this stuff into a CMOS fab, but no one had ever done it before, and a lot of the devices had never been made. Like high-speed modulators in silicon didn't exist when we started Luxtera, and that's a keystone component. No one had ever built silicon photonic chips that had both optics and transistors on them. Like it was sort of tabula rasa. So, I really don't deserve much credit for this stuff. Like I was one of the founders, but like the credit for this goes to the team that implemented this. Like they figured out not only how to build it, but how to find a product to be built out of this that the market would actually absorb and get excited about. And that was an incredible achievement. So I stuck around, while we did the first couple of tape outs there and got some of the basic technology working, and I did a bunch of the prototyping. But then I decided to go back to grad school. And so I did a bunch of nonlinear optics in grad school. I ended up taking a job at University of Washington as a faculty member. Ended up splitting my time between UW and National University of Singapore, and then eventually between NUS and University of Delaware. I got tenure. We spun off a couple of companies that were doing design services and government contracting and things like that. Bootstrapped those from scratch on, with customer projects. At the time, I was running an institute at the university called OPSIS, which was taking silicon photonics and abstracting doing the same thing that TSMC did for microelectronics in essence, which is taking the devices and abstracting them into some basic mathematical models for the devices and into what's called a PDK, which is basically a set of building blocks, Legos that you can put down on the chip, fit them together, and use those Legos to build any of a variety of different systems. And so we had a couple hundred users around the world who were running silicon with us in order to build systems across a wide variety of different applications. We started having customers, companies coming to us who wanted to build things but didn't have a team. And so that was how we built this design services activity that was called SLS. We sold SLS to a private equity firm called Marlin, with the intention of bringing it in-house within one of their portfolio companies called Corient. It was a big telecom company. I recruited a bunch of my students. I resigned from a tenured faculty position and decided to go do that. I had recruited a person named Larry Schwerin as our CEO, who had far more experience and was far better as a CEO than I was. I ended up as the CTO in that organization. We spun that off, moved the team to New York, and ended up building 3 generations of product, 100G, 200G, and 400G transceivers for telecom networks, as well as coherent, as well as data center transceivers. We did a data center chipset, sold a bunch of that stuff, did a lot of innovation on packaging, a lot of innovation on chip design, developed our own process for building the chips. And at a foundry, we developed a lot of new design software. That company was acquired eventually by Nokia, became the optical subsystems group at Nokia. And so those chips and those transceivers are now in metro and long line systems and DCI systems, data center interconnect systems all over the world. So that's kind of cool. And I was at Nokia in a CTO role for about 2 years, a little under 2 years. And then I joined a startup called Luminous that was building AI supercomputers. I'm now doing an incredibly poor job of being retired. I'm failing at retirement. And so Nowadays, I do some consulting, I do some advising, I do some sitting on boards, and I'm mostly focused on getting back to my roots in the world of geopolitics and geostrategy and technology policy, things like that.
Well, sounds like a really interesting portfolio of insights and technical skills. And before we go to some of your most recent pursuits, let's at the beginning of this conversation, we spoke about silicon photonics being one of the highest growth industries that most people have never heard of. So for non-technical audiences, help us understand exactly what the product is, sort of why is it important, how do we think of it in the value chain of the broader hardware sector today?
Yeah, so when you think about microchips, most people, when they think of microchips, they think of the kinds of chips that go into say, a CPU from Intel, or the chips that are in their cell phone, or the chips that are in their Xbox, right? And those are microelectronic chips built mostly by Intel or Samsung or TSMC that are cutting edge scaled CMOS. The 3 nanometer chips, 5 nanometer chips, 7 nanometer chips. These are chips that have billions of transistors on them, and I don't mean that. I mean that literally, billions to tens of billions of transistors. Or you go to Micron or Samsung or someone like that, and you'll buy your RAM, which is your memory that goes into your computer or goes into your cell phone, and those chips are a very big, very mature industry, but they're not the whole chip world. In fact, they're not even close. If you look at in terms of dollars, or in terms of numbers of chips, most of the chips you buy are not deeply scaled CMOS, right? The chips that are in your monitor are high voltage chips that run the display. Those are not done in 7 nanometer. They're done in more trailing edge processes. Could be 130, could be 250 nanometer. And these are things that were very cutting edge in terms of the lithographic line width, the size of the devices. These were cutting edge 5 years ago, 8 years ago, 10 years ago, 15 years ago. But it's not like those folks stop innovating, right? They've continued to add features and capabilities. And so, if you want to do super high speed analog, you might go to a place like Global or Tower and get bipolar chips, which are a different technology from CMOS and allow you to get very, very high bandwidth RF devices without having to go to super narrow line widths. So there's lots of diversity, even just in the electronics world. And then there are chips with MEMS in them for making accelerometers and gyroscopes, little mechanical moving masses. There are chips that are used as light sources. That you make an indium phosphide or gallium arsenide, where it's not even silicon, it's some other semiconductor material, and use it to make lasers, right? Or LEDs, right? The LEDs in your light bulbs are probably gallium nitride or indium gallium nitride, which are these more exotic materials. But the fabs that make those make, hundreds of thousands of wafers a year of light emitting diodes, right? It's not transistors, it's a different thing. But it's the same base technology. It's the same kinds of machines. It's the same ways of manufacturing things. It's all based on printing structures on wafers. It's just like a printing press, but for building nanoscale devices. And it's actually very similar to a printing press in a lot of ways. So, the silicon photonics was started out as this idea that was mostly baked in an academic setting, where the idea was, well, historically optics was always done in these exotic materials platforms, indium phosphide, gallium arsenide, lithium niobate. You'd use lithium niobate to make your modulator, you'd use germanium to make your photodetector, you'd use indium phosphide to make your light source. And the thought was, well, all right, what if we could do some subset of this stuff in the same materials that you use to do scaled CMOS, right? In the same, literally the same fabs, the same materials, the same wafers that you use to make transistors. Because if you could put the transistors on the chip, or at least electrically very close to the chip, you could do all kinds of cool things because you could move signal back and forth between the electrical and the optical domain very seamlessly. And so what Luxtera did was they built the first process where you could do transistors and all of the optics except the light source right in the silicon. And that was a major advance. And what we've seen since the early 2000s is that, and I wrote this up, God, it must have been in the mid 2000s. I wrote up a paper on this where we showed that the doubling time for silicon photonics was somewhere around every 9 months, where you would double the complexity of the chips, which is much faster than Moore's law, right? Moore's law at the time was around every 18 months. Nowadays, it's slowed down a little. And the reason for that is that with Moore's law, every time you need to build a new generation of chips, you have to build a more advanced fab that supports narrower line width, which costs about twice as much, right? So a modern fab at TSMC costs tens of billions of dollars. I mean, it's really expensive. Plus the R&D to actually stand it up, which is similarly expensive to actually develop these processes. For silicon photonics, we were never line width limited, right? So, the electronics folks had built these fabs that could build incredibly complex things with amazing process control and super narrow line width that was far more than what we needed for the silicon photonics. And those fabs were just there. And all we needed to do to access them was to make something compatible and to convince the people who ran those fabs that there was a business to be made in running photonics. And that second part, convincing that there was a business to be made in it, that was a hard problem, right? And that took years. And it took many, many tries by many, many people across a whole community to get to the point where now silicon photonics is the default technology. Like down to like 2015, 2016, 2017, if you went in pitching an optics project to someone who was knowledgeable in the industry, it could be an investor, it could be someone who was a GM at a big optics company, and you say, "Oh, I want to do this in silicon photonics," they would say, "Why? Why are you doing this in silicon? There's all these other material systems. You can make a better modulator in lithium niobate. You can make a better light source in indium phosphide. Like, why are we doing this in silicon?" And there were a few people who were visionaries who saw the benefit of building high complexity systems on chip, some of whom were at those companies, some of whom were investors, some of whom were folks who did their own startups, who said, "Yeah, we can see why you do this. We're gonna pursue this." But it was a very small minority of the people in optics. Nowadays, you go in and pitch a new project at any of the big companies in optics, whether it's an end user, like a network equipment manufacturer that's buying modules and that's putting them into the network, or whether it's a hyperscaler who's actually deploying this stuff, or whether it's someone who's building transceivers, and you go pitch them on building something, and they'll say, what's your integration strategy? Is this silicon compatible? Can you run this in a standard process? And if you're saying, well, I'm doing this, a new material, they'll say, well, is there some way to integrate this into a silicon platform? Is there, how are you going to manufacture this at scale, and make it compatible with the silicon chips, silicon photonic chips that we're already building, because they all have teams doing this stuff. And so it's become the default, right? And that doesn't mean that it's the only way to do things. There's lots of other materials platforms out there where people are either integrating them with the silicon photonic chips, or where they're trying to replace things that you could do in silicon, but they can get better performance in one dimension or the other. There's lots of integrated optics platforms that have come after, where they're supporting lower volume applications that are very performance oriented. But if you look at like what's going into the data center, you look at what's going into the telecom systems, nowadays that's dominated by things that are silicon photonics run in CMOS compatible foundries. And that's a thing that has happened over the last 20 years. It's been, I would love to say that, this is something I saw coming 20 years ago, and I was just super clever about picking the right thing. And I can't say that, right? Like I many of the people around me and I as well had the vision that this was something that could happen and that we hoped would happen, and we put a lot of effort into making it happen. But I think we as a community have been fantastically lucky that this worked out, right? And that it turned out that this could all be done, and that the demand showed up for high complexity optical chips. And that the hyperscalers started building out massive data centers that needed hundreds of thousands of transceivers, and they needed them to be super cheap and needed to be low power and high performance. And like, that was not a thing back in 2000 that any of us would have called, right? Like the early applications for this stuff were things in supercomputing, that sort of thing, right? And so, we on the one hand, I think we as a community did some smart things, and we there were a lot of good ideas and a lot of smart people who did a lot of hard work to make this happen. But there are a lot of communities where all of those things are true, and you don't get lucky by having the demand show up for the thing that you're building. And so, especially when you're starting with technology push rather than with market pull, which you have to do if you're going to do something that's going to take 5 or 6 or 7 years to build, or at least you often have to do. It's easy to end up in a situation where you've done fantastic technology, but the market doesn't show up for it. And so it's one of the reasons that I always tell people who are starting out as entrepreneurs that you really have to spend as much time as you can talking to customers and talking to potential customers and identifying what does a customer even look like, right? Because there's lots of people who are interested and who will say nice things, but are not willing to write a check, right? A customer is someone who's able to write a check, right? And getting to the point where you can give them an excuse to write a check is your job as an entrepreneur.
Yep. So speaking of the reasons to write a check, what are some of the most interesting applications of this technology that you see today? And then what are some of the other possible future applications which may need something else to enable it or to make it more?
So the initial applications for this technology were data center transceivers, moving data along the 100-meter, 2-kilometer links, where you tie together the boxes and the racks in a data center. The second generation applications were things in the metro and DCI and to some extent long line systems, where you're doing telecom infrastructure to tie together different facilities across longer distances, tens of kilometers up to thousands of kilometers. And those were the two areas where this technology really got proven at commercial scale for the first time, right? And there were a whole series of startups in both of those spaces that got acquired. Luxtera and Elenion were 2 out of probably close to 10 that were built and acquired across the span of about 10 years or so. There was Kotura. Acacia got picked up by Cisco. There were a whole bunch of them, right? It was a big blossoming of the field, right? Nowadays there are tens of startups. It wouldn't surprise me if there's 100 silicon photonics startups out there. Might be more. And it's so many that I can't even keep track of all of them. And I talk to the people in this field all the time. There's a lot of startup activity. And what's interesting is now that silicon and integrated photonics is not regarded as an absurd idea. It's regarded as sort of the default idea for new projects where you want to drive down the cost of optics and drive down the cost of complexity. Now there's all sorts of interesting projects, and there have been a few of these. Like I think the first silicon photonic biosensors companies got started many years ago. Kerry, our former CTO at Luxtera, Kerry Gunn, he started Genelite, which is still going, which I think was the first silicon photonic sort of clinical biosensor company. There was another one that got started.
Tell us what's an example of a biosensor. When is it used? Why is it exciting?
Yeah, so if you want to be able to diagnose medical conditions by looking at the reactions of sensors on the surface of a chip and quantify medical data, um, that's what you would use a biosensor for. And the nice thing about silicon photonics is you can build big arrays and do lots of stuff in parallel. There was another one that came out of University of Washington that I helped them get started, that was called Sidex. They didn't make it, but they did a lot of really interesting stuff, right? There's a whole generation of biosensor companies out there in silicon right now. There's one called Scifox. I believe they're based in Boston. There's a whole series of them in Europe. I mean, the nice thing about silicon as a photonic platform is you can do high levels of integration really cheap, which means you can make many sensors. You can build everything that you need to interrogate those sensors on the chip. And because you have the optics on the chip, you can have very, very sensitive measurements. The challenge is, of course, always the biology, right? Putting down the chemicals in a controlled way, having very good selectivity for what you're looking at on the surface. That's almost always the hard part, right? But there's a whole generation of optical biosensor companies on silicon and associated platforms that have gotten going. There's really interesting applications that are still very early to things like quantum communication. One of the big challenges is, if you can build quantum computers, how do you make it possible for the quantum computers to actually talk to each other and share quantum information, right? Because if you have to convert it to classical information, then you lose a lot of the value, right? So there's a bunch of companies that have gotten going that are looking at support using integrated photonics and silicon photonics to support quantum communications. There's a couple of them out of Maryland and out of MIT that are doing really interesting, cool stuff. There's been a lot of activity on LiDAR, laser radar, where you want to do essentially laser range finding, but with angular resolution, so that you can see how far away things are. Initially, there was a lot of interest in that for the automotive world. The automotive world is a tough business to get into. You have to be very reliable, very cheap, and able to live in a very hostile, harsh environment. And so the automotive adoption has been slower than people expected, but there's a whole lot of other applications for LiDAR out there, from drones to security to airframes. Knowing how far away you are from things is generally a useful thing to know how to do, and being able to do it at high speed through fog and through obstructions and things like that is valuable. And so, there's a number of ways to do it. You can do it with cameras, you can do it with LiDAR, you can do it with radar sensors, you can do it with ultrasound. I think a lot of systems in the future will be multimodal. You'll be synthesizing a lot of these different sources of data together, and silicon photonics is a great way to build LiDAR systems, and to build not just the front ends where you steer the beams, which can be done with silicon, or they can be done with moving mirrors, but doing the back end where you actually process the light, and you generate the light, you process the light, you do the signal processing. That's all very much in the silicon photonics realm. There's a lot of people doing various kinds of RF photonics, some of it for military applications, some of it for signal processing for the cell phone networks. So, anywhere you need to do really high speed linear signal processing, there are applications for silicon photonics. There's a lot of people trying to use it for optical compute. I think there will be applications someday for optical compute, but it's a really hard problem, and it's something where it's still in the science project phase right now. But
give us some of the examples of optical compute. What would that?
So optical compute is just trying to do the kinds of computations that you now do with electronic silicon that you buy from NVIDIA or from Intel, and building processors that actually do that computation in the optical domain. Historically, there's been very limited success for that sort of thing, because optics is intrinsically linear, whereas transistors are intrinsically nonlinear. And so, having a set of switches that you can just program in the electronic domain has a lot of power, and that's the main computing paradigm today. Optics is more, it's more suitable for situations where you need to do a lot of signal processing, things like Fourier transforms or other kinds of linear computations, and where the nonlinear part is a much smaller part of the computation and is not the main bottleneck. Now, there's no, to my knowledge, there's no optical compute that's ever been deployed at commercial scale. And there's some very exotic things like image recognition systems and things like that, but it's a technology that's been in the lab for 2 generations now, for the most part. There are some intriguing possibilities for doing optical compute, especially for applications and things like AI. And there's been a lot of controversy in the community about whether or not optical compute is really going to be a solution for them, because, frankly, no one has shown that optical compute can solve the scales of problems that you need to solve to be useful for AI right now. There's beautiful papers. I've participated in some of them out of, for instance, Dirk England's group at MIT, where proof of concept for this kind of thing has been demonstrated. There's beautiful science that you can do with this stuff. Eventually, I suspect that there will be applications for optical compute, but that eventually could be 20 years out, right? It could be 5 years out. I don't know how to make a call on that yet. But there's definitely a lot of very smart people working on it who are very excited about it. It hasn't gotten there yet. There's chemical sensing applications. There's satellite communications applications. There's free space communications applications. Anywhere where someone needs to manipulate light with great precision, there you find integrated optics and silicon photonics almost invariably as one of the technologies that people are working on.
So, Michael, you've worked with a couple of your co-founders for a long time across multiple companies. What are some of your reflections on how to find the right co-founder and how to make that partnership the most effective?
Great question. So one of the things that I think a lot of people get wrong who are doing their first startup, sometimes even their second or third startups, is they don't recognize the essential difference between co-founders and early employees. The boundaries between these two things can get a little bit blurry in the sense that, a very early employee who has a big equity stake looks a lot like a founder. To me, the distinction is that the founders are the people who join something early enough that they're not getting paid. They're joining before there's capital, before there's revenue, and they're being paid either solely or almost exclusively in equity. And then eventually when money starts coming in, they should make a reasonable industry salary. So it's about appetite for risk. Now, one of the things that I've seen again and again is that people do not do enough diligence on their co-founders. You have someone who's come up with a great idea. They meet someone who knows more than they do about some area that's important for the company. But given that they know nothing, knowing more than they do might mean knowing a trivial amount and just being able to fake it.
And so how do you do your due diligence? What are some of the secrets of running the most efficient due diligence process?
Yeah, so my experience is you work with people for a long time. I mean, I've worked with the same people across multiple companies. I work with people who have shown that they're trustworthy across many, many, many projects. And yeah, that's a hard thing to do when you're doing your first thing, but you want to do as much diligence as you can. And so if you're talking to someone about being a co-founder, especially, and separating from a co-founder is always traumatic. Most startup companies are more intense and last longer than a lot of marriages, right? And so the ways that you do diligence are, number one, spend some time working with the person before you bring them in as a co-founder. talk to the people they've worked with before at length. Ask them, and you can't ask them, is this person a problem? Because, very few people want to say something negative, but you ask them indirect questions. Well, what are the ways that I could work with this person to help them? What are the areas where I can help them improve? What are the areas where I can help them, where they have things to learn? What are the areas where what are some instances of situations where you had to step in, right? If you ask for a qualitative, is this person good or bad? You'll almost always hear good, right? No one wants to badmouth someone. But you want to ask very specific, very tactical, open-ended questions. And you want to do it in person if you possibly can, so that you can measure the person's reaction and look them in the eye. And you want to do really in-depth reference checks on people who've worked with them extensively. And you really want to spend time with a person and work with them and have them deliver something, see them deliver something before you bring them in as a co-founder. What you want from co-founders is people who don't need to be managed. You want people who are going to be able to be successful at complex things without a lot of supervision, and where if they don't know what to do, they're going to come back and they're going to talk to you and they're going to brainstorm and they're going to figure it out. You don't want people who are going to need a lot of management.
And are there any types of feedback that you may have gotten on someone that, people would generally think of as less positive, but you were actually very comfortable with that negative feedback and that it being okay?
I mean, there are people whose feedback I trust and people whose feedback I don't trust. I guess what I would say is, if you dig deep enough, you can always find someone who won't have perfectly positive feedback about a colleague, right? But it's a question of how deep do you need to dig? How many people do you need to talk to? And what's the substance of it? And is it anomalous or is it consistent? You'll find 9 times out of 10, if people have concerns or hesitancy, it's consistent across multiple people, because most people don't change that much over time. Like, they make the same mistakes again and again.
That makes sense. And so then once you've selected your co-founder and you've worked with yours for many years and many different companies, presumably there were some situations that you disagreed on. Some of them could have been really big decisions. So how do you navigate those situations?
It's really difficult. One of the things that I've seen that's really important for founders is, and I tell people this when sort of teams get together and they talk to me about this, you have to anticipate, if you have a group of founders, that you're going to lose some of them at some point. And so you should structure the contracts and the economics in such a way that if someone has to leave, either because they're not delivering or because there's a disagreement or because they have a life event that's outside of work that means that they just can't keep doing it for whatever reason, that they can leave and everyone feels like the outcome is economically fair, right? And that's a difficult thing to achieve. But it's really important to structure vesting and responsibilities and all of that stuff so that if that happens, because statistically, if you have 4 or 5 founders and you have something that takes 4 or 5 years, the probability that one of them is not going to be with you at the end of that 4 or 5 years is very high. The other thing is that you should make sure that you sit down among the founders and talk about what does success actually mean, right? Because everyone says, "Oh, I'd like to make a lot of money," but you go around the table and you say, "What does a lot of money mean to you?" And for some people, it means I want to be able to, put a down payment on a house, right? For some people, it means I want to make $100 million. For some people, it's anything short of Elon Musk's scale success doesn't count. And those are often incompatible goals. Not always, right? Sometimes they're compatible because there's ways of finessing it. But if you have 2 of 5 founders who mostly care about delivering amazing technology and are not money oriented and, just want to make a reasonable living and, be able to buy a house someday. And you have another two founders who stand to inherit a pile of money, and anything short of $100 million win they don't care about. They're going to have very different ideas about what risks the company should take and what makes sense in terms of economic outcomes. So sitting down and having a conversation about what does success mean for you is something that you rarely see founders do because it's a really sensitive topic, but it's really important for understanding where your co-founders are coming from when it comes to making basic economic and risk decisions.
But then how do you manage this dispersion? For example, in our portfolio, we have a number of companies which have this heavy, science component to them. And I find that their founders are very much motivated by the opportunity to create something new, contribute to, innovation. They have a big mission behind it. And that's a very different type of motivation. So when you have people on your team who just want to achieve that, go to space, build something interesting, or, find their next scientific discovery versus somebody else who wants to build a profitable, large company, how do you manage that difference?
Every team is different in terms of how you manage it. But as a CEO and as a founder, the first step to managing it is to understand what people's motivations are and to check in periodically because people's motivations may change. People's thoughts about this stuff may change over time. It's also really important to make sure that everyone on the team, and especially everyone on the founding team, feels like they're getting something valuable out of the experience, even if the company doesn't make it to a positive economic outcome, right? They need to be learning something. They need to be gaining experience that is valuable to them. They need to be doing something that they find challenging and interesting. Because the worst thing, well, I don't know if the worst thing, but one of the worst things that can happen is to have founders who have a big stake in the company, maybe they even have a board seat, who don't believe in what's going on, but are still there and are in one way or the other not bought into what's going on, right? And so, and that goes for employees as well. Like I'd rather have someone tell me, I'm not bought into this anymore. Let's talk about a transition plan, and hand off what they're doing in an organized way to someone else, or even just not have the job getting done, than have someone doing the job who doesn't believe in it. Because if you don't believe in it, you're going to do a bad job, right? The belief in what you're doing is an essential part of being successful as a startup, and having everyone on the team bought in and believing in the mission and in what you're doing and in the leadership, that's the superpower as a startup, right? I mean, that's an essential characteristic if you want to defeat incumbents, right? Yep. And so, if you have people who are not bought in, you need to have a clean way for them to exit. And in a world where startups often have to pivot and change what they're doing, and there's going to be disagreements, you need to anticipate that and structure the company so that if there's a disagreement and people can't disagree and commit, and sometimes you can't, right? Sometimes there's a disagreement where you can't, you just don't believe in what's going on anymore. It's important to work with people who are going to say that up front and organize a transition rather than sticking around and just doing a half-assed job.
Yep. And continuing with the theme of alignment of interest, how do you think about the type of a VC or other type of investor who makes a perfect capital partner for a business like yours in the semiconductor optics space?
Yeah, I don't think this is specific to my domain. I think having investors and board members who are very smart, very well connected, and very aligned to the mission as understood by the founders and the executive team is crucial, right? Because the investors it is frequently the case that especially first-time entrepreneurs sort of think of all investment money as being fundamentally fungible, right? And it's not, because with that money come people who sit on your board who you're going to be talking to and looking to for guidance and looking to for additional injections of capital in a lot of cases for years and years to come. And so the people you're putting on your board and your principal investors, you want them to be people who, when you don't know what to do, they're your first call. Not because you have to call them, but because they're people whose opinions you're going to respect and who are going to have things to say that can, where you don't have to go spend a bunch of time polling a bunch of people to try to figure out how to deal with the problem. They've dealt with the problem before. They've seen it 10 times before. They can tell you, here are the five options for dealing with this problem. Here's my recommendation. Here's the second best option. Let's talk about how it applies to this situation. Because they're going to be up to speed on what's going on at the company, and they're going to be deeply interested in its success. And they may disagree with you, but they're going to be very much on the team, and they're going to be people whose advice you want. Right? These are, the board is there to help you, not just to do a board meeting periodically and sign off on the financials and stuff. The board is there. They should be your first line of people you go to for counsel and for help and for advice. And that's what you want from a board.
Look forward to our next conversation on this topic. Michael, thank you for joining the interview.
My pleasure.
Thanks so much for listening to the Village Global podcast. You can check us out online at villageglobal.vc. We'd love to hear from you, your feedback, your ideas, your inspirations. You can email us at hello@villageglobal.vc.